they won't be able to see it. All right. Okay. So good afternoon, everyone. So welcome to the guest session that we are hosting today. So we have Dr. Julian, who is joining us. So he's an astrophysicist and a programmer from the University of Nottingham. So he's here to give us a good understanding about the topic dark matter and dark energy. So welcome, Mr. Dr. Julian. Nice to have you with us for the third time.
Thank you for inviting me.
All right. Okay. So kids, will be so Dr. Julian will be talking about the dark matter and dark energy. So once he finishes, there's going to be a Q&A, question and answer session for you guys to ask questions from him. Right. So during the question and answer session, each and everyone will get an opportunity to ask a question. All right. So Dr. Julian, are you ready?
Yes, I am. So
all right.
Shall I?
Dr. Julian, over to you.
Okay. All right. Let me just share my screen and talk to you a little bit about dark matter and dark energy. So this is a rather frustrating topic because we kind of know there is something out there called dark matter and dark energy, but we don't really know what it is. So what I'm going to talk about is why do we think this mysterious thing exists, or these mysterious things? If it does exist, what could it possibly be? Because we're not really sure. And if there is something out there, how can we go about finding it? So this is a big problem for us at the moment because we really don't know what we're doing. So we're really hoping that somebody will come up with an answer. So it could be one of you that could finally solve this mystery, because we don't really know what the answer is at the moment. What we do have is quite a lot of evidence for what is going on. So this is what we think the universe is made of. If we take the whole universe and put it in a pie dish or something like this, this is how it would be split up. So this little bit in blue here, I don't know if you can see my cursor, but I'll change it to a laser pointer. So this tiny little bit in blue is what we call atoms. So that's what makes up everything. Makes up you, it makes up me, makes up the room I'm sitting in, the computer, the atmosphere, the planet, the sun. Most of the things we can see in space are made up of atoms. And that's what we studied in astronomy for many, many years. It's, we studied stars and planets and things like that, and they're all made up of atoms. But then in about the 1980s, we started to find out that wasn't all there was to space. There's something that we called dark matter, and that makes up about a quarter of the universe. And we don't really know what it is, but we sort of know how it works, if that makes any sense. We sort of know how things work for it, but we don't really know what it is. And then in about the year 2000, we found out not only was the dark matter, but there was this thing called dark energy, and that makes up nearly 3/4 of the universe. So it's been a bit embarrassing for astronomers. We've been studying just 5% of the universe for most of our history, and it turns out there's a lot more to the universe than we realize. So how did that come about? So this was first thought of in about 1932. So that's over nearly 100 years ago that we first started to think there could be something wrong. And we're still waiting to find out exactly what it is. So if you're hoping to find the answer to what dark matter and dark energy are, I'm afraid you're going to be disappointed, because we really still don't know. So we're hoping that somebody, or some students or some researcher, will finally work it out. But let me tell you where we've got to at the moment and what we know. So if we look at cosmology, so there's astronomy, which is studying stars and planets and things like that. Cosmology is a sort of branch of astronomy that studies the entire universe, absolutely everything, but as a big system. So it would be like studying the world rather than studying, a small country or a river or something like that. It looks at the whole world and how the whole world is formed. So cosmology looks at how the universe is formed and how it started, how it's going, perhaps how it's going to finish. And in cosmology, what everybody, more or less everybody, there are a few people who don't, everybody starts from this model, which is called lambda CDM. So that's a confusing mouthful of letters. So lambda is a Greek letter. That's this Greek letter here, lambda, and CDM is the other one. So if you look into almost anything, this is it, lambda and CDM. And CDM stands for cold dark matter. So you can see dark matter is very much present. And this lambda is actually just, it's a mathematical term, but that stands for dark energy. So this is our current model of the universe. It's made of dark energy and dark matter. So let me just explain those a little bit more. I just picked out a few papers here, but you can see lots and lots of papers talk about this lambda CDM. So that's what a lot of astronomers are talking about. So what is it? So lambda comes from Albert Einstein and his equation for gravity, which is a horrible equation. I'm going to put it up here, but you don't worry, you won't understand it, because I don't understand it either, and not very many people do. It looks fairly simple, but it's incredibly difficult to solve. If you ever go into sort of really deep mathematics, you'll find out how messy this equation is to actually solve. But there are two parts to it. This left-hand side says how space curves. So if you put down an object like a big star into some space, space bends around it. And this bit of the equation says how it bends. And this bit says how matter will behave. So this says how stars will go around other stars, or planets will go around stars, or things like that. It's all a bit very complicated. But right in the middle is this lambda term right here. And he put this into his equation and said, I don't really know what it is, but it seems we need it. So this is where the lambda comes from. And I can't really explain much more about it than that at this point from the equation, because I say it's a very, very complicated equation to actually solve. But what we did think of, so we found this dark energy, I say it takes up about 75% of the universe. And the first thing physicists thought of was that there is a thing called vacuum energy. So if you take a big box and you take everything out of it, everything you could, all the air out of it, all the atoms, everything out of it, so there's nothing left in it, then you will have a vacuum with nothing there. But there is still energy within that box. And this comes out of some rather deep quantum mechanics, which I won't bore you with, but that seemed to be a possible answer to this dark energy. This could make this dark energy. And what does dark energy do? It pushes things apart. It's a pushing force, but it's a very, very weak pushing force. So it pushes apart very distant galaxies. It doesn't really affect you or me. It's a very, very weak force. So it doesn't really push me away from you. It doesn't really push the Earth away from the moon or even the stars apart in our galaxy, because the gravity of our galaxy is strong enough to hold it together. But where it's allowed to build up between galaxies, it starts to push them apart. So we thought vacuum energy might be one of the possible answers to this, but it turns out it's not, because if we actually calculate it, which we can, it turns out to be wrong by this amount. So that's a huge error. I mean, not many people make such a big error. So it turns out that it's vastly wrong. So that was our best guess at what dark energy was, and it turns out to be wrong, or at least we can't see a way to make it right because it's wrong by such a big amount. You know, if it was wrong by twice, we could perhaps find a way of halving it. But when it's wrong by this much, it's very difficult to come up with any idea. So if any of you come up with an idea, I'd be really interested to hear it. So we started to look at other forces and come up, and this is where we're basically making things up. So we're making up ideas and then trying to test them and see if they're real. So one of the ideas was something called quintessence, which is a fifth force. So we have four forces that we know of. There is the strong and weak nuclear force, electromagnetic, and gravity. So those are the only forces we know. So we come up with a fifth force, which people have called quintessence. And this might be what dark energy is, but as I say, we don't really know. So the big summary of dark energy is we sort of know something is out there, but we have absolutely no idea what it is. That is really what everything comes down to. We have this dark energy and dark matter, and they are completely different things. They just happen to have a very similar name. But dark energy we know almost nothing about, except how it affects very distant galaxies. Dark matter, on the other hand, we do know a little bit about, because we've been studying it for a bit longer, and we've come up with ideas about what it could be. So I've sort of told you everything we know about dark energy at this point, which is not very much. So that's a big thing we've got to sort out over the next few years, hopefully. Cold dark matter, though, that one, I say, we do know a little bit about. We really don't know what it is yet. You can't go down to a shop and say, can I have a bottle of dark matter, because we don't know what it is. You wouldn't know what to put in the bottle. So why is it called cold dark matter? It's firstly called cold because in physics, when we talk about cold, that's usually about how fast things move, like atoms and so on. So if you get something very hot, the atoms are moving very quickly. So cold dark matter, we think the whatever it is that makes up the cold dark matter is moving fairly slowly. It could be moving faster than you or I can move, but it's not moving at very, very high speeds, particularly at the speed of light. So that's what some ideas were, that maybe it was moving a bit like light or other things that move very, very quickly, but we think it doesn't. We think it moves quite slowly compared to other things in nature. Why is it called dark? This is because we can't see it. At least we can't see it by light. It doesn't matter how much light you shine on it. It will never respond to light. Light just goes straight through it. So this is why it's very difficult to see, especially in space where we see everything with telescopes. So we can't see it because it just doesn't affect light. Light just goes straight through it. It would be like a window pane. You know, if the glass in a window pane is perfectly transparent, it doesn't matter how much light you shine on the window, all the light goes straight through the window. We don't always have a perfect glass, but that would be an example of it. And why is it called matter? not really clear on that one. It's just because we think it is little grains of stuff that are floating around. So that's sort of why we come up with matter. But it's not a particularly good word for it because when it was first come across, nobody knew what it was, and we still don't know what it is. But we have a better idea of what it isn't, in a sense now. So this is what the universe was when it started out. So when the Big Bang happened, which was about 13.8 billion years ago, there was a lot of dark matter around then. In fact, about 63%. So about 2/3 of the universe was dark matter when it began. You can see there's no dark energy there in this original thing. Dark energy grows over time. So the bigger the universe gets, the more dark energy seems to occur. And where we are now is that you can see there's a lot of dark energy because the universe has got a lot bigger. The dark matter is still about the same amount compared to the amount of gas and atoms and things like that that we know about. So where did all this come from? Why did we think to make this up? I mean, we don't just make things up for fun. We have to have some evidence for it. So this is where it started from. And about 1932, so I say nearly 100 years ago, this famous scientist called, astronomer called Jan Oort, he was born in the Netherlands or Holland, and he was quite a famous astronomer. He has a few things. There's an object called the Oort cloud, just out beyond Pluto and Uranus, Neptune, just about beyond that, and he discovered that. So he's more famous for knowing that. But at this point, he was looking at the galaxy, where we live in the galaxy, where our star is in the galaxy compared to all the others, and trying to work out, were we on the edge of the galaxy? Were we right in the center? Were we somewhere else? And he worked out in the end that we were somewhere in the middle of the galaxy. But he said there's a bit of a problem here. We don't seem to have enough stars to keep us in our place. We are going around and around the center of the galaxy every about 250 million years, but we're going around too fast. There aren't enough stars to hold us into our place. So we should be flying out of the galaxy. So he said, that's awkward. I don't know why that is. So he left it there. He went on to do other things, but other people took it up. And this character here called Fritz Zwicky, who was a bit of a wild character. He was very, very clever, but not particularly easy to work with, I don't think. But anyway, he looked at some things. He looked out in space at this cluster here. This is a group here of galaxies. You can see all these things here. These fuzzy things here are all galaxies all around there, but they're all held together as a group. And he could weigh that. He worked out a way to weigh how much all these galaxies weighed, but he worked it out by two different ways. One, by looking at the light that comes from those galaxies. He could work out using a not very complicated mathematics exactly how many stars there were in all these galaxies just by looking at how much light they put out. And he came to a big number there. It's about a trillion times the weight of our sun. So about 1 trillion suns he thought were in there. But he could also weigh it by looking at how the galaxies moved around each other. And when he weighed it by that way, he came out with 100 trillion. So there is about a factor of 100 between the two ways of measuring it. So he came up and said, well, this is 1933. He said, well, there seems to be a lot of dark material that I can't see. So there's a lot of dark matter that is holding this thing together that we can't see. It's not shining with any light, but it must be there to hold this thing together. Otherwise it would just fall apart. So that was about 1933. And I have to say, not many people did very much with that after that time for quite a little while. But then we started to look at other things. So this is looking at our own solar system. So we have the sun right in the middle. And then we have the planets, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and Pluto is not really a planet anymore, but we can put them on. And this little graph here says how fast do they have to go around the sun to stay where they are. So you can see Mercury has to go around really, really quickly because it's very close to the sun. It feels the sun's gravity. And if it didn't go around quickly enough, it would fall into the sun. So Mercury has to go around very quickly. So it goes around in about 88 days. It goes whipping around the sun very, very quickly. And if it went any slower, it would fall into the sun. And you can see Venus doesn't have to go around quite as quickly because it's a little further out, and Earth goes around in about a year, and Mars goes around in a little longer than that. And as we go further and further out, by the time you get to Pluto, that is so far from the sun that it doesn't really feel the gravity very much. So it can go around very, very slowly. It takes about 238 years to go around once. So if you lived on Pluto, you would only have a birthday every 238 years, which would be a bit sad, I think. So that is how it works out for the solar system. And we can use the same mathematics to look at galaxies. And when we look at a galaxy like this one, this is a nearby one called Andromeda. When we look at that, we can work it out by mathematics. And this is what we would expect to see, that the stars inside go around fairly quickly. And then as we go further and further out, they go around slower and slower and slower, a bit like Pluto and Uranus and Neptune. But when they actually turned the telescopes onto these stars and started measuring them, they saw something very different. This is what they actually see, that the stars keep speeding up and they keep going faster and faster. So that was a big difference between what was expected and what was seen. And to correct that, you'd need about 5 times as much stuff in this galaxy as we can see. So that was a problem. And then another case is, this is some work that I've been involved in a little, that if you make a simulation of the universe, you make a model in a computer of the universe and you put everything in and you sort of mix it up and let it run and see what it turns out to look like. If you just put matter in and you don't put any dark matter in, then you let it run and you come out with something that looks a bit like this at the end. It doesn't look like that. It doesn't look like a real universe. When we look at what our computer simulation of the universe looks like, it doesn't look anything like the real universe. But if we put in a lot of this stuff called dark matter, we don't know what it is, but if we put something in that sort of pretends to be something very similar, then, and put in about 5 times as much as we put in regular matter, then we do get a universe that comes out that looks very similar to what we see with our telescopes. So that seems to be another indication that we're not quite, that we need this dark matter to get things to work out. Now, another one, this comes back to Einstein, and he said that if you get very heavy objects, they bend light around them. So we know that is true. We've seen light bent around the sun and other heavy objects. And we can see that out in space in particular places where you happen to get 2 things line up. So here is this is a galaxy not too far away and a very, very distant galaxy. And here we are on Earth looking at it. And because this makes a big dent in the universe, light bends around it like this. So if you look from Earth to past this, you actually see several images of this galaxy because it's like a big lens that is bent around this. And we can use, I can't, but other people who are clever at maths than me can use Einstein's equations to work out, well, how much is the light being bent and how much would we need to be sitting here to bend the light by the amount we're seeing? And yet again, it turns out you need about 5 times as much stuff as we can see bending it. And if you want to see what one of these looks like, this is what what we call a gravitational lens looks like. So this is the nearby galaxy, this orangey thing here. And this is the very distant galaxy, but it's all spread out. It's all bent around this other galaxy. So we're seeing it very distorted because all the light is coming around this galaxy that's far away and coming to us. So we see a few of these. We don't see very many of them because they have to be lined up almost perfectly. what we do see more is things like this. This is a cluster of galaxies. These are the ones that are nearer to us. You can see all these fuzzy yellow things, but you can see these streaks. Perhaps you can see these streaks of light. Those are very distant galaxies being bent around them. And if you're very good at maths, I have a colleague who is very good at this sort of maths. You can actually undo that and you can get a picture of the original galaxy. And the final really big indication that there is something missing came from this picture. And this is a picture of the universe in microwaves. So the same sort of thing that you get in a microwave oven. It's a sort of radiation between infrared, which is heat, and radio waves. So somewhere in between those two. And if you take a picture of the night sky in that, which is very hard to do, you can't do it from Earth very easily because the atmosphere blocks a lot of it, but you can do it from satellites, and this is from a satellite. You can actually work out by looking at this. Again, I can't, I'm not very clever at this sort of equation, but some scientists are very, very good at looking at this sort of picture and digging information out of it. And this is the sort of information they dig out of it. They get a graph like this, and this graph tells them, and I can't exactly explain how they get this because there is some very complicated maths in it, but this tells us several things. This big spike here tells us that the universe is flat. Now, what's flat mean for a universe? It used to be thought that maybe the universe was curved, a bit like living on the Earth. If you start off from one place and you just walk in the same direction forever around the Earth, you will come back to where you started because it's a big ball basically, and you walk right way around and you come back to it. And we used to think maybe the universe was like that. If you were in a spaceship and you shot off in one direction for a long time, you would eventually come back to where you are because it would be like a big ball and you would just go right round it. But anyway, this work from this satellite says, no, it's not. It's flat. It's like a sheet of paper. If you set off in your rocket across the universe, you will never come back to where you started with. You will just keep going forever and ever and ever, at least as far as we know. So that is one thing that came out of this work. But they also came up with these two things, these two peaks here, these two spiky bits, mean something special about it. And this says how many atoms there are to how many dark matter. And yet again, it comes out about 1 to 5. So we have several things that seem to point to this thing called dark matter existing. So there are two possible ways we could be wrong about the universe. One is we don't understand how gravity works. So if we don't understand how gravity works, maybe that would sort things out. Maybe Einstein was wrong and gravity doesn't quite work the way we think it does. But that's a very difficult idea to keep because gravity works extremely well according to the equations we use. We can use it to go to the moon. We can use it to go to Jupiter and Mars and places like that. And it works extremely, extremely well. We've tested it to many, many decimal places of precision, and it seems to always work. So when you've got something that works that well, it's very difficult to change it without breaking everything. So it's very difficult to change our understanding of gravity without just breaking everything that works. So that's why we decided that maybe there was a lot of missing stuff out there that we don't understand. And we've given various names to it. There are things called machos, there are things called neutron stars, there are things called black holes, there's extra gas, and there are things called brown dwarfs. Now, all of these things we understand. These are all sort of just heavy lumps of stuff like planets and suns and stars. But we can't find enough of these to actually make up the missing material, not by anywhere close to the amount we would actually need to correct the universe. So we don't think any of these things exist in big enough quantities. There might be a few of these things floating around, black holes and neutron stars. We're almost certain there are plenty of those floating around, but not nearly enough not by a long, long way. So it's a long way off from that. So what does this look like? This is a picture of a galaxy very similar to ours, and we would be somewhere about here in this picture. This is where the sun would be. This is the center of the galaxy, and this is the very outside. So we would be somewhere about here, somewhere in the center of it. So you can see all the sort of stars here. Each of these little plots are stars, and this is a spiral galaxy, so you can see the spiral arms of it. But if we could see the dark matter, we would see that actually it was quite tiny, that the actual galaxy, if we could see all the dark matter, would be much, much bigger than what we could see. And if you looked up in the night sky, so here's a picture of a night sky with a crescent moon. The nearest galaxy to ours, similar to ours, is called the Andromeda Galaxy. And if you could see it in all its glory, it would look about this big. So you can see it's actually quite a bit bigger than the full moon. But unfortunately, it's very dim to our eyes, at least. You can see it quite well in telescopes, but we can't see it nearly as big as that on the night sky. But if we could see it, then this is how big it would appear. But if we could then look at the dark matter around it, we would see this huge purple blotch around it, which is all the dark matter that is part of this galaxy. So it would be about 10 times as big as the actual galaxy. There would be a lot of this stuff floating around. And I don't know if you'll get this quick joke, but this is what we like to think of. We call these dark matter things halos. So we think maybe if you're a saint and you have a halo above your head, maybe you have a big dark matter halo. Now this is an example of what would happen in our galaxy. So this is a computer model of our galaxy spinning around like this. And at 500 million years, they take away the dark matter, and you see what happens. All the stars, apart from those right in the very center, go flying out. So if you took away the dark matter from our galaxy, it wouldn't hold together anymore. Just the very center of it would, and the rest of it would go shooting off, including us. We would all go shooting off. So we do need the dark matter to keep it there. So that sort of explained why we think it exists. And there are other more sort of technical reasons, which I won't go into, why we think there is this thing called dark matter. And it would be all around us. It would be in the room with you, and it would be touching you and going through you. But it tends to go through absolutely everything. So it doesn't really bump into you very much. So what could it be? We know it's probably not, we're almost certain it's not anything that we would recognize as atoms. So it wouldn't be just another element like hydrogen or oxygen or anything like that, because we would be able to see it if it was. So we've got other possibilities, and these are all very much made up. So people have come up with ideas and said, well, it could be this, it could be that. And we've given them names. One of the most popular is called a WIMP. It stands for Weakly Interacting Massive Particle. So this is a massive particle that doesn't bump into other particles very much. It goes through you, almost like a ghost. And some popular ones for those is a particle called the neutralino, which you've probably never heard of because very few people have, because we don't know actually whether it exists at all. We also have something called the sterile neutrino, but we don't know whether that exists. We have another particle called the axion, and we don't know whether that exists, but all these are possible reasons for dark matter. Another particle called graviton, and then we have all sorts of strange things that people have made up. So there are all sorts of strange things, and they sort of sit on this big chart here with possibilities for what they could be. And some of these things are very, very heavy. So they could be black holes was a very popular idea. They're very, very heavy. And then things over here are very, very light, incredibly light. I can't explain how crazily light they were. Now, some of these things come from very interesting areas of physics. So one of them comes from something called supersymmetry. And this is the idea that the stuff we know the stuff that makes up atoms and molecules. I don't know if you've heard of those things, but they're called quarks. They are, if you split up an atom into bits, you come down to neutrons and protons. And if you split neutrons and protons up, you come down to quarks. And these are the quarks over here. So one idea is that maybe these all have like an almost twin particle of a slightly different form called supersymmetry. And you come up with not only that, but you come up with this whole other set of particles. And these are called quarks over here, and these are called squarks because they're supersymmetric quarks. And there's the electron here. This is called the selectron because everything gets an S on it, except the things that carry force. So these are the things that carry force. This is the photon. That's what carries light and also electromagnetism. This is the gluon. This is the Z and the W. So these, when you break things right down to their very basics, this is what you come down to. There aren't many basic things. But over here, you get a similar thing. You get something with enos added on. So this is the photino and the gluino and the xeno and the weno. So that was one possibility. And lots of scientists thought maybe this would be correct. This would be the answer. And if so, you could get this particle made out of these things, these SUSY particles, supersymmetry particles, and it could be called the neutralino. Now, they've looked long and hard to try and find any evidence of any of these, and so far we haven't found any evidence of it. So we're not really sure whether that is the case or not. Another one is called the axion. This has been around since 1977, and another idea. Nobody's found one of those either. A sterile neutrino. This is like a particle that we already know, but also doesn't exist, or we haven't found any evidence for it. And in fact, the evidence for this has got weaker. There's an experiment that went looking for it and hasn't found any of that, so it might not be that. Then there's a whole lot of other things, including string theory and so on, that have gone looking for it, and other types of things. So what we're left with is we're sitting in the middle here wondering what it could be. And we have all these possibilities. It doesn't matter what they are, but there are all these possibilities for what it could be that people have made up. They said it could be this, it could be that, it could be that, it could be this, it could be any of those. And so far, we haven't found any evidence that any of these things actually exist. So it's all a bit frustrating and awkward at the moment. So we really need some clever people to come along and come up with new ideas. But how could we actually find it if we wanted to go looking for it? And obviously we have done some of this. So the first way is to actually try and make it. So this is a picture of the Large Hadron Collider, a very big science experiment in Switzerland, which sends beams of particles shooting around a very big ring. And this is actually it from the air. So you can see it's 27 kilometers. You go all the way around here. So they send particles racing around that very, very fast, and then they bang, crash them into each other. And when you crash them into each other at very high energies, sometimes you get new particles appear. So they've been doing that for many years now and looking to see if a new particle appeared, a dark matter particle appeared. And so far, there is no sign that it's appeared. They've been looking very hard, and they're about to have another go at looking. But so far, they haven't managed to make one of these things. And that could be because there's two possibilities. Maybe it doesn't exist. So they're banging these things together, hoping that one of these would appear, but it hasn't. That's one possibility. And the other possibility is they're just not banging them together hard enough. Perhaps if you hit them together even harder, you would get one of these things to exist. But they're at the limit of their machine that they made at the moment, and they haven't found any so far. So it probably, they don't think they'll find it with this machine. They would need to either build a bigger machine or come up with a new idea. Now, another way you can try and find it is you can have a little dark matter detector, or quite a big dark matter detector actually, and you can try and detect these bits of dark matter, which must be floating around. There must be hundreds of them or millions of them actually in the room that you're in, but they don't really bump into other things very much. You know, I can clap my hands together and my hands bump into each other, but if they were made of dark matter, they would just go through each other because they don't really feel each other very much in a sense. They're so tiny, they just pass through each other. But they might occasionally bump into each other. So this is one possibility. And to find these things, they take these detectors very deep underground into the deepest mines we've got, because there's all sorts of stuff coming down from space, these cosmic rays, and they would mess up the signal. We would just detect lots of cosmic rays rather than the dark matter. So they build them deep underground in these mines, and you have to go down almost a kilometer or more sometimes deep underground to get to these places. And this is a sort of dark matter detector that they've built and tried to detect them. And what they're hoping for is they've got this big vat of stuff in the dark matter detector, and just once in a long, long while, a dark matter particle will come in and it will bump into an atom. But it's very, very rare event. They think it will perhaps happen once a month. So you'll wait for a month for this to happen, and it might or might not happen. And so far, they haven't managed to find any particular evidence of this. It's a very hard job to do because you're waiting, I say, for about one of these things to happen a month. But in the meantime, you get lots of fake things that happen that aren't dark matter, that are just regular matter bumping into them, and they look very similar. So you have to disentangle them. So we haven't found those yet. This is another experiment. This is looking for something different, and they're keeping it very cold, but they're looking for a different sort of dark matter here. They're looking for the axion particle. And this has a secret that if you have a very strong magnetic field nearby, some of these particles can turn into light. So they're looking basically for light that's coming through this. And yet again, they haven't found it. So there's a lot of people looking for this stuff and nobody has found it. So there's a big experiment out there waiting for somebody clever to come up with a new idea for finding it. And the third way we're looking for it is to look deep into our own galaxy and see if we can see signs of dark matter behaving deep inside our own galaxy. And yet again, we haven't found anything there that could be explained. So we're a bit stuck now, and we're coming up to the place where we don't really know whether this dark matter is real. We never know whether it's really a particle because we don't know what it could be. We've got lots of ideas, but none of them seem to be working out. So there are other ideas, and an Israeli astronomer came up with this idea that we could change the equations and we could come up with something called MOND, which means changing gravity. But this is a rather complicated slide. I'm sorry, I shouldn't have kept this in, but it's an interesting idea. Not many people think it could work out at the moment, but it's another way of looking at it and saying, well, gravity doesn't work quite how it does, but on the scale of galaxies, it works in a slightly different way. So that's one possibility he's come up with. So let me finish there. Cold dark matter is the bit we understand most out of dark matter and dark energy. We really don't understand very much about dark energy, but is it cold? It probably is. It probably doesn't move very quickly, if at all. Is it dark? Dark is a very bad word for it. It really should be transparent or something like that. And it doesn't really behave like matter. So let me finish with that. And one other possibility is that it's this is a silly slide, but perhaps it is just coffee that holds the universe together. So thank you very much for listening. I don't know how much you found that gave you any insight into this, but happy to take any questions you got on that.
Thank you very much for that, Dr. Julian. I hope the kids could get the answers that they had for the questions and doubts that they were having for a very long time. So we have a few kids who have raised their hands. I guess they have questions to ask. So we'll start off with Sudhita. Hello, Sudhita, you may unmute.
Why is dark matter very transparent.
Why is dark matter very, sorry, I didn't get the last bit.
So he was like,
Why
why is it
can't-
transparent?
Why is it transparent?
Yeah.
Yeah, we don't really know, but it has to be, otherwise we would have seen it by now. So that is one, it's a very good question. And we don't really know why it's transparent, but it just does seem to be, because we've looked really hard with telescopes to see if we could see it, but we never have. So, and we can see it by other ways. We can see it by the way it affects other stars. So if you've got a really heavy thing here that you can't see, then it will make other things move around it, that they will be attracted to it. So that's kind of how we see it. But as to why it's really transparent, that comes down to sort of the quantum physics of it, why it doesn't work with other particles, and that's a really messy topic to get into. So I don't really have a very good answer for you. It's a really good question, maybe one that you could answer. Maybe in 10 or 15 years you could be a famous physicist and work out the answer to that. If you do, please let me know, because I would like to know.
Thank you very much, Dr. Julian. Next, we have Bina.
Can dark matter come to another planet like Proxima Centauri, but is undetected?
Yeah. We think dark matter is almost everywhere. So it's all around our planet, all around our sun. It's around Proxima Centauri, Alpha Centauri. All the stars in our galaxy are covered in dark matter. But because you can't touch it and you can't see it, it's a bit mysterious. We don't really know, as I say, what it is, but we think it's everywhere. It's passing through you even now, we think. So that's a bit weird, but it never bumps into you. It just goes straight through you. It's much like a ghost almost. It just moves through you and out the other side without you feeling it.
All right, Dr. Julian. Next, we have Nivan.
Excuse me, Dr. Julian. If we can see dark matter, what do you think it would look like?
What do I think it looked like? It would look like, I think it would look sort of like an ocean of stuff that we were sitting in. So it would be like the sea almost. It would be like a big spread out thing, but it wouldn't be like particularly sharp or angular. It would be very smoothed out and very flat. So I think it would be like you sitting in a boat in the middle of the sea. You just see this big sea all around you. So yeah, I would love to be able to see it and see what it looked like, but we can't see it with our eyes, unfortunately. We can sometimes see it in computers. When we make models in computers, we can color it in, because we can color it any color we like, and then we get these big sort of seas of dark matter, because it's very fuzzy. It's not like a metal or a pottery, which is quite sharp and has sharp edges sometimes. It's very like I say, like the sea. It just spreads out everywhere. It doesn't particularly come into sharp bits. Very good question. Thank you very much for that one.
Thank you, Dr. Julian,
Doctor.
for answering. Next, we have Imalkar.
When the universe dies, is dark energy will dark energy echo of the universe?
All right. Well, we don't really know what's going to happen when the universe dies. There are 3 possibilities, and dark energy features in most of those. That's a really good question, by the way. Thank you for that. So because we really don't understand what dark energy is, we can just come up with ideas. So one idea is that the dark energy stays much like it does at the moment, and we just understand it. And that would just push things apart very slowly. So everything will get further and further apart. So the distant things we're looking at right now, the distant galaxies, will get further and further away. And if we come back in millions and millions, well, in fact, billions and billions of years, then the universe will get darker and darker because everything will be pushed further and further away and we will never get to see very much of it. So that's one possibility. Another one for the end of the universe is that dark energy, gets less strong over time, and the universe would then collapse in on itself. And we started with a big bang with everything shooting away from each other, and if it changes, then everything would come back into each other, and we'd end up with something called the big crunch, when everything comes together. We don't think that's probably going to happen now. We think that is probably not a possibility. But if you hear of the big crunch, that's what that is. And the other possibility is that dark energy gets stronger and stronger over time. So it's pushing things apart very, very gently at the moment, but it could get stronger and it start to push things even harder and harder and harder. And if that happens, then it will start to get strong enough that it will start to push planets away from their suns and the moon away from the Earth. And then it will get stronger and stronger, and it will start to push, mountains and things apart. And eventually it will push atoms apart, and everything will get ripped apart by this really strong dark energy. We don't know whether that is the case, and it would take trillions of years. It would take such a long time for that to happen. But if it did, that's another possible end to the universe. And that one's called the Big Rip, because everything is ripped apart. So we have the big crunch where everything crunches together, the big rip where everything rips apart, and then this other one sort of in between where everything just fades away slowly. So very, very good question. Thank you very much for
that. Thank you for answering, Dr. Julian. Next, we have Arudit.
This is me, Julian Onions. Are black holes related to dark matter and dark energy like?
So our black holes, yeah. So black holes we kind of understand those. We've seen pictures of black holes, so we sort of understand those. They are very big. They're the ends of very big stars, so they suck everything into them, and they do suck dark matter into them. So dark matter does fall into black holes and disappears, but it doesn't. Dark energy doesn't really worry about that. That would still push black holes apart eventually if it went to this big rip idea. So that's a good question. We don't really understand exactly how those things are going to work out in the end. We're still learning about black holes. At least we can see black holes. They're quite difficult to see, but we can at least see them. We know what we're looking at. With dark matter, we don't really know what we're dealing with. So until we know what it really is, we don't know how it will work. So we'd like people like you to grow up, become astrophysicists and sort all this out for us.
Thank you.
We have another question. Is the universe black color because of dark matter?
No, the universe is sort of, well, it's mostly dark because there isn't enough stars to light it up completely. So it's not really the dark matter that does that. The dark matter does have a big influence on the universe. It makes the universe how we see it, but because we can't see what it is, we don't really understand quite why. Thank you for that question.
Thank you for that, Dr. Julian. Next, Ayusha.
Excuse me, Dr. Julia, when our universe will be exploded, will atoms and dark matters would be there?
Yeah, well, It's very, very difficult to explore our universe at the moment because we can't travel fast enough. It takes a long while to get anywhere in the universe. I mean, it takes about 3 days to get to the moon. It would take about 9 months to get to the planet Mars, and it would take thousands of years to get to even the nearest star with the current engineering. So we need some we need some very clever engineers to get with better space rockets so that we can explore it. But if we did explore the universe with spaceships, maybe something like the Star Trek Enterprise or something like that could jump very long distances, I think we would still find dark matter everywhere. So yeah, dark matter is going to be everywhere we look, I think. It's just everywhere. It's a bit like water on the Earth. It's sort of everywhere, even when you don't think there's any water. If you dig down, sometimes you find water. I think we would be like that. We would just keep finding more and more dark matter.
Excuse me, Dr. Juliet, I have another question. If some people say that our universe is expanding, when our universe expand very big, will it collide with another universe?
Oh, that is a very good question. That's a very good question. So some people are thinking that is a possibility, that there isn't just the universe we live in, but there are other universes that sort of exist outside of what we can see. It's a very difficult question to answer, though, because we have no idea how to tell if there is another universe. So until somebody comes up with a good idea to say, well, how can you tell? You know, I can tell if there's a screen here because I can actually go and touch it, but we don't know even how to touch another universe. So some people have come up with ideas that could be the case, but we really don't know of an experiment to work out whether those things exist. But if it does, then that could be a possibility. And some people have come up with the idea that black holes, the black hole might be forming other universes within it. We don't know how likely that is or not, but people come up with all sorts of crazy ideas, and some of them will be right, some of them will be wrong. And until we can find out a way of saying, is this idea right or wrong, we don't really know how to make any progress on that. So thank you again. That's a really clever idea. And maybe you'll be the one to sort that out. Who knows?
Thank you for that, Dr. Julian. Binal, got any questions?
Yes, sir. If the universe blasts into two pieces, will dark matter appear within another planet? Will take place where the dark matter will be seen?
Yeah, so if you split things into half, or if you broke things apart, I think you would end up with, if you sort of split the Earth in half, you would have two half Earths. You would get as much dark matter in one half as there would be another. You would split the dark matter into two as well. I think. I can't say for certain because we don't, as I said, we don't really know what dark matter is, but we think that is how it would behave. If you split things into halves, you would halve the dark matter too. So that is what we think. But until we really know what it is, we can't say with any certainty that is definitely how it will happen. But that is kind of what we are going with at the moment. That's what we believe at the moment.
Okay, thank you.
Thank you for the question.
Thank you for that. So I think that's all. So is there anyone else who wants to ask a question?
Some very good questions. Thank you very much for those.
Vishal, yes.
Yeah, yes, sir. Is dark matter similar to gravity?
Yeah. When we simulate dark matter, we just simulate the gravity of it, really, because that is the only way we know how it works at the moment. So we just follow how the gravity works out. We assume that it has the same sort of gravity as regular matter, but there's a lot more of it, so it gets a lot more gravity. So yeah, that is a very insightful question. Thank you.
And another one, do white holes have dark matter?
That's also a very interesting question. So white holes would be the opposite of black holes rather. Black holes suck everything in. White holes just pour stuff out continually. They are an idea that has come out of the equations of Einstein that they could exist. But so far, we've never seen any indication of a white hole existing. They should be quite bright things because they would be pouring stuff out all the time. And so we think that they would be really fairly easy to see, and we haven't seen any yet. But if they did, they would probably be pouring out dark matter too. So, yeah. But up till now, we haven't seen any evidence for white holes. They are just an idea somebody had. Well, Einstein had, I guess.
And another.
Yeah.
Yeah. After supernova, does the dark energy spread all through space? After supernova.
Dark energy, we think, is just everywhere in space. It's like if you have a box of space, it has a bit of dark energy in it, and if you have another box, it has a bit of dark energy in it. It doesn't sort of move around. It's just with the space. So if you get some space, you get some dark energy. You get more space, you get more dark energy. It's not like dark matter, which is more like, say, water or something, where you could pour it from one box into another. Dark energy just is part of the space. But that's just what we think at the moment. But as we don't really know what it is, we can't say whether that's true or not.
Excellent. That's all. Thank you. Thank you.
Thank you very much for those questions.
All right, kids. So thank you very much, Dr. Julian Onions, for helping out these kids, and you have answered a lot of questions. I believe most of them have got the satisfied answer that they were expecting. So, so Dr. Julian, so before we end the session, I just want to know, like, what do you think of today's, this session? What do you think about that?
There's been some very clever questions there. So you have some very bright people there. And that gives me hope that maybe we can sort this out, that a couple of you, or maybe all of you, can work out what these big challenges are. As I said, 20 or 30 years ago, we didn't even know some of these things existed. Now we think they do exist, but we need somebody to work out what they are. So we're looking to the future now. I don't think it's going to be me who works this out. So I'm going to hope some of you are going to work this out. So come and join us and work out exactly what dark energy and dark matter are.
All right, that's nice to hear, Dr. Julian. I really hope that would happen one day too. So, so Dr. Julian, so thank you for joining us for the third time, and I really hope that you will join us in future as well, because we have a lot of batches that we have, that are coming up in near future. So I really hope that you will be able to join us even then. So yes, thank you very much for accepting the invitation again. It was really nice of you. So thank you very much, Dr. Julian. It was enlightening.
Thank you very much. Hope you have a good day. Goodbye.
Goodbye. See you.
Bye, Dr. Julian.
Bye. Bye, Dr.
Bye, sir. Bye.
Bye, and thank you for the questions.
Bye, Dr. Julian.
All right.